All right, so let's talk about Lasso and Elastic Net, which sort of build on the ideas that we talked about last class with ridge regression. So, as a review from last class, what are we minimizing with ridge regression? We're minimizing the residual sum of squares, like we are with least squares, plus this penalty, where the penalty is lambda times the sum of the betas squared. So what's the resulting estimate for beta hat ridge? Well, you derived this in the last class and hopefully got this. X transpose X plus lambda times the identity inverse times X transpose Y. So why is this useful? This is useful because, as we mentioned, sometimes it's impossible to transpose X transpose X. And so having this additional penalty makes that transpose possible. And it also helps just when the x's are highly correlated. So in cases where the x's are highly correlated, you're going to end up with large variance. And that's not always ideal. And so this basically is a shrinkage method that can help kind of with that variance problem when you have highly correlated variables. Okay, so how is this lambda or this penalty term determined? So that penalty term is basically determined by some kind of bias-variance trade-off. So we use some method, for example, cross-validation, to sort of balance between the bias and the variance and find kind of that optimal lambda accordingly. So this is a real take-home message for this class, is that the bias-variance trade-off, this is often what we're dealing with. We're trying to sort of trade a little bit of bias basically we sacrifice a little bit of bias to get a little bit of a better variance, and kind of back and forth in that manner. If we were looking at a picture of something like our mean squared error or our root mean squared error across various lambda values, we would essentially pick the one that minimizes that test mean squared error or that test root mean squared error. And so we would expect that similar picture that we've been seeing so far, where you have kind of this U shape, where on either end, when you're either not very flexible or very flexible, you have higher test mean squared error, and in the middle somewhere, you've got this nice sweet spot of this trade-off that we're trying to optimize. Okay, so ridge regression. The pros are it can be used when P is greater than N, so when you have more predictors than you have observations. It can be used to help with multicollinearity. So even in the case where, even if your x's are not perfect linear combinations of each other, so X transpose X is possible to invert, sometimes they're highly, highly correlated, which can really inflate your variance. And so this can help with that. And so as lambda goes to infinity, your variance is going to get smaller. Of course, if we have pros with all trade-offs, we also have some cons. And so it's going to have an increased bias compared to least squares. In the previous lecture, we talked about we quantified exactly what that bias would be. And it doesn't really help with variable selection. And that's because all the variables are included in some regard, even if their beta coefficients are really small. So the way that ridge works is basically it's going to shrink those beta coefficients down so that you don't end up kind of blowing up your model with these highly correlated coefficients. But all of the variables and all of the potential predictors are going to have some value in your model. It might be very, 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 very close to zero, but they're going to have some value. And so that's important to remember, because if you're trying to do variable selection where you can actually fully remove certain variables from your model, ridge regression is not going to help with that. So in comes the lasso. So the lasso is similar to ridge, but it actually drives some of those beta coefficients to zero. So it drives them to actually be equal to zero, which helps with variable selection. And so sometimes when we're fitting a model, if you have tons of variables, tons of predictors, and especially in the case where P is greater than N, we want to be able to maybe decide which variables are key to our model to be able to select which ones that we need to sort of focus on. And so that's where variable selection can become really important, and Lasso can be really helpful with that. So as I stated, ridge is not helpful with variable selection. It is helpful with shrinkage, but not variable selection. Lasso actually drives some of those beta coefficients to be 0, and so it basically drops those variables from the model and thus does variable selection for you. So this is the penalty for lasso. So we're still minimizing our residual sum of squares, but now we're adding this lambda term times, and this here is the absolute value of beta j. And so we say that lasso uses what we call an L1 penalty, and ridge uses an L2 penalty. And that's because basically this is like an L1 norm and L2 norm. This is kind of how we can write those. So the penalty, the sum of the absolute value of beta, is going to be equal to this L1 penalty, and the sum of beta squared, that's going to be equal to this L2 penalty. So like ridge regression, lasso shrinks the coefficients towards 0, but unlike ridge regression, it actually shrinks some of them to be exactly 0. Basically, it forces some of the coefficient estimates to be exactly 0 when the tuning parameter lambda is sufficiently large. So when you've picked a big enough lambda value, some of those coefficients are going to be shrunk all the way to 0. And so therefore, as I mentioned, lasso can be used for variable selection, which is very useful. So lasso, basically, variable selection helps us create smaller, simpler models. It helps us create what's known as parsimonious models, and so that's basically a model that's small and simple, and this is generally a good thing. Choosing lambda, again, is done via cross-validation, so the same method you'd use to pick lambda for ridge, where we're dealing with this bias-variance trade-off, where essentially you're sacrificing a little bit of bias to improve the variance. So, the pros of lasso. It can be used when p is greater than n, so it can be used when you have more predictors than samples. It can be used to help with multicollinearity, so just like ridge. It will decrease the variance. As lambda goes to infinity, the variance is going to decrease. So as you increase your lambda value, you're decreasing your variance. And it can be used for variable selection. So since it will make some of those beta coefficients be exactly 0, it can be used for variable selection. So the pros here are exactly the same as ridge, except we've got this one extra pro here that variable selection is a possibility with lasso. The cons, same as ridge, it is going to have increased bias compared to least squares, because as we're increasing that lambda value, our bias is increasing, which again is that bias variance trade-off. So we're sacrificing some bias, we're increasing the bias in order to decrease the variance. Another con is that if p is greater than n, lasso can select at most n variables. So it's never going to select more variables than there are samples. And so what that means is that regardless of what your lambda value is, you're going to be dropping at least, the difference between p and n variables. They're going to be shrunk all the way to 0. It's just going to be how the model forces it to happen. Okay, so ridge versus lasso. Neither ridge nor lasso are going to universally dominate, so there's not like one that's always better than the other. Cross-validation can actually also be used to determine which method should be used. So if you don't have a reason, if your goal is variable selection, then obviously lasso is the preferable one. But if you don't have that goal, if you're just trying to fit the best model, or the model that basically has the smallest test mean squared error, smallest test root mean squared error, if that's your goal, and again, remember that we're back in a continuous outcome land here with ridge and lasso. These are both methods that are done specifically on continuous outcomes. So we're going to be using root mean squared error or mean squared error as our test, as our way to assess how the model's doing. And so if the goal is just to fit the best model possible, sometimes the best model is going to be ridge, sometimes it's going to be lasso. And you can imagine creating these cross-validation samples and trying your model using ridge, trying your model using lasso, and you could compare the results accordingly. Cross-validation is also used to select lambda in both methods. And so you choose the lambda value for which the cross-validation model is the smallest, which basically means that, by which I mean that has the smallest error. And so in R, we are often going to be looking at the root mean squared error. And so you would do your cross-validation, you would look at a variety of lambda values, and then you do what we call tuning by picking the lambda value that minimizes that root mean squared error. So sort of finding that sweet spot of bias variance trade-off. Okay, so what if we want to do both? So what if we want to kind of allow for more variables to be included in the model than samples? But we also want to make sure that we're doing some shrinkage all the way to 0. So we're doing some variable selection as well. Well, it turns out there's a statistical method for that. It's called Elastic Net. And so this is what Elastic Net looks like. It should look pretty familiar. Essentially, we've taken the root mean squared error, which we're still using to minimize. That's if we set lambda 1 and lambda 2 equal to 0 here, these two pieces would drop out, and we would just be looking at root mean squared or the residual sum of squares. And so the residual sum of squares is that thing that we're minimizing in least squares, and also in Elastic Net if both the lambda values are 0. Now, if lambda 1 is equal to 0, so we cross this part out, we would have just lambda 2 times the absolute value of beta j. And what would that be? Well, that would just be Lasso. And if lambda 1 is 0, so that's if lambda 1 is 0, then we just have this term, we're just doing Lasso. If lambda 2 is 0, we just have this term. And so now we're doing ridge. We would just have the residual sum of squares plus lambda 1 times the square of sum of the squares squared betas. So Elastic Net basically just takes that residual sum of squares and it adds two penalty functions, the penalty for ridge and the penalty for Lasso. So what is the L1 part of the penalty? Well, remember L1, that corresponds to the to Lasso, and so that's going to be this part here with lambda 2. And what is the L2 part of the penalty? That's going to be this part in the middle here, the part that looks like ridge. So when would this be equivalent to ridge regression? We just sort of talked through this a little bit, but this is going to be exactly equivalent to ridge regression. So remember, ridge regression is the residual sum of squares plus lambda times the sum of the squared betas. So this is going to be exactly equal to ridge regression if our lambda 2 is 0 and this term drops out. And for Lasso, it's going to be the opposite. It's going to be exactly equal to Lasso if this middle term drops out, meaning if lambda 1 is equal to 0, this middle term will drop out, and this will be exactly equal to Lasso. So the L1 penalty part of the penalty is going to generate a sparse model. So what that means is it's going to shrink some of the coefficients to exactly 0. So yay, this is doing our variable selection for us. This is basically acting like the Lasso. So that L1 part, or this part here that corresponds to the lambda 2 times the sum of the absolute value of beta j, that's going to be generating this sparse model. The L2 part of the penalty removes the limitation on the number of variables selected. So now the number of variables selected can be greater than n. So that's exciting as well. So that's what this part here does. The ridge part basically removes that limitation that the number of variables selected has to be less than or equal to n. So how do you think lambda 1 and lambda 2 are chosen? Cross-validation. So like we would do for all the other methods, you're basically going to create a grid of potential lambda 1 and lambda 2 values. And you're going to search across that grid using your cross-validation samples. And you're going to pick the pair that minimizes the 2.